So, as I was saying, for oil fluid samples, the experiments that are being carried out in the routine laboratory tests include compositional analysis, followed by constant composition expansion, differential libration experiment, viscosity tests, and sometimes separator tests. No CVD, which is constant volume depletion. That's for gas. Replace DLE with CVD for gas samples. Hope it's clear.
Yes, yes, sir.
So composition analysis, let's start by explaining the first one, which is the first experiment that's been carried out, because when you receive your sample, you have to understand what's within that fluid. We do this to accurately determine the composition of the reservoir fluids. Some people are still struggling with their network. Providing critical data for reservoir modeling and performance predictions. The importance of this composition analysis is to closely approximate the original reservoir fluid, especially when sampled early in the reservoir's life. It also provides the most complete description of the fluid and its constituents. So the key parameters measured include the separation and quantification of components from methane through hexane, heptanes and heavier components grouped as a single component with average molecular weight and density being measured, essential for phase behavior and volumetric calculations. So this compositional analysis is being done using the gas chromatography equipment. It is being used to determine the composition of the reservoir fluids, including hydrocarbons and impurities. First, you obtain fluid samples using surface or downhole sampling techniques. The sampling method, there are usually two types. You either collect your samples at the separator, and at the separator, unfortunately, the gas has already been liberated out of the oil. So which means you collect your gas sample and then oil sample, then you combine them so as to get a representative of the reservoir sample. And there's also the downhole sampling technique, whereby they collect the sample at the face of perforation before the gas even liberates out of the oil, which is actually the best, but either way, you can still work with it. So the next thing is to analyze the sample using gas chromatograph, separate the hydrocarbon components by boiling points, since each of the components have its own boiling point. Identify and quantify gases and heavier components, then record molecular weight and density for the heavier components from the C7 upwards. So the next thing is to validate the results you get, comparing them with the known industry standards. So this is an overview of how you should expect your results to come in a PVT report. For the composition analysis, this is how it looks like. For surface sampling, this is what you should expect. You will see the liquid sample in percentage mole and the gas sample in percentage mole. And when they recombine them, it will give them this small percentage, which is the reservoir fluid representative. And if you see it, whenever you sum it up, it should be always equals to 100. If it's not equals to 100, it means some components are missing, thereby affecting the integrity of your sample. So unfortunately, if you use that for your analysis, you might not be analyzing the representative of what's within your reservoir. And to my right is also a composition analysis result, but for a bottom hole sample. As you can see, you just get the reservoir fluid percentage mole directly, because in this scenario, you don't have to collect the gas sample, oil sample, recombine it back to get a reservoir representative sample. This is why you collect the reservoir representative at the face of perforation. That's why you will have only one column. for the reservoir fluid in mole percentage. And also, it must also be equals to 100. So then we move to the constant composition experiment, expansion tests. The reason why this test is being carried out is to simulate the pressure volume relationship of reservoir fluid at constant composition. The purpose of this experiment is to determine the bubble point or the dew point, which is also called saturation pressure. Also to calculate the isothermal compressibility above saturation pressure, also to measure the compressibility factor, which is Z of the gas phase, and also to assess the total volume of hydrocarbon with respect to each pressure step from initial to atmospheric pressure. So the experimental procedure is after collecting the fluid sample from the field guys, you put it in a PVT cell, you subject it to reservoir temperature and reservoir pressure. How do we do this? Subjecting it to reservoir conditions. How they do it is they put the fluid sample in a PVT cell, which looks like this. It has a transparent glass where you can have visuals on the fluid sample. This is mercury. Mercury is being used to control the pressure steps. So if they subject it to the reservoir pressure, they pump in more mercury till it reaches the desired pressure step they want to start the experiment. And as they remove it or eject it out, they are like mimicking a pressure depletion step. Let's say from 5,000 to 4,500 to 4,000 to 3,500 pressure steps to bubble points down to atmospheric pressure. So they keep on adjusting the pressure steps, thereby recording the total system volume of the oil at corresponding pressure step until they reach saturation pressure. At saturation pressure, this is when you first get your first bubble of gas. You record that volume also. Then you continue decreasing the pressure by ejecting out the mercury from the PVT cell up to the atmospheric pressure. But after recording all the volumes for the respective pressure steps, how to get your relative volume? We usually have this formula, relative volume equals to the volume at each pressure step over the volume at bubble point, at start. That's bubble point. So as they are doing the experiment for each pressure step, they keep on recording the volume of the hydrocarbon for each respective pressure, including that of the bubble point. But for you to calculate the relative volume, you take each volume of the pressure step and divide it by the volume for the saturation pressure, or let me say bubble point pressure with regards to oil. So thereby getting, after that, you identify the saturation pressure. Oh, we have crossed that. I think I've explained all this. And the next thing is to give you an example of how the results comes out of the lab. This is the relative volume. And as I said, this is the formula to calculate it. After getting the volume for the respective pressure steps, you get the relative volume. For each of those steps also, they calculate the compressibility factor and also the Y function. The compressibility factor usually for the gas that liberates, and the relative volume for the total fluid. So this is a typical example of how you see a CCE report. Your pressure in PSIE, in field unit, and also in metric unit, and also the compressibility factor in field unit and metric unit. When we start the PVT modeling, you'll appreciate the plot. The plot is there's actually a close relative volume values before bubble point and actually a steep increase after bubble point. But when we start modeling, we get to understand that more. The next experiment is differential libration experiment. And the differential libration experiment simulates the reservoir depletion to determine the shrinkage of oil, the gas-oil ratio, the density of the fluid, visibility also, and I think that's all. So the main objective is to understand how gas liberates as pressure decreases. The importance of this is to represent hydrocarbon flow behavior above critical gas saturation. The key data measured, which I have earlier stated. The experimental procedure is also close to that of CCE, but not 100% the same. The difference is that when gas liberates, you take your readings for the respective properties for both the oil and the gas that liberates. No, sorry, let me not mix things up. When you reduce the pressure from the previous pressure step, you let it calm down, let the gas liberate. After liberating, then you eject it out. You eject the gas out. If you eject the gas out, then you measure the properties of the.
Sorry, Ibrahim, are you there?
Yes, sir. Is my mic off?
Yeah, I didn't hear you.
For the differential libration experiment, can you hear me?
Yes, we can hear you.
When you collect the sample from the field guys, you put it in a PVT cell, subject it to reservoir pressure and temperature. Just like the CCE, the experiment will be run on pressure steps up to atmospheric pressure. But the difference with CCE is that when gas liberates upon reduction in pressure, the gas will be ejected out. Then you measure the PVT properties of the fluid that remains within the PVT cell, such as the GOR of that fluid, the formation volume factor, the oil density, and so on. So when you subject it to the next pressure, gas will liberate again, then you eject it out. Remember, in CCE, you will not eject the gas. The gas will remain in the PVT cell. But in the differential libration experiment, the gas will be ejected out, thereby moving to this step. Then you what? You reduce the pressure again by ejecting out the mercury out of the PVT cell, leading to what? Liberation of more gas. When it liberates out, what will you do next? Then you eject it out. The oil that remains, you measure the corresponding PVT properties such as GOR, formation volume factor, oil density, and so on. You record it, then you move to the next pressure step until you reach atmospheric pressure. This is how the results looks like. Measure the GOR, the density of oil, and the formation volume factor of oil. Also, they calculate the residual oil relative density at standard conditions and also the API of the fluid. So when you receive your PVT report from the PVT lab guys, this is what you should expect as your DLE results. And if, as you notice, the GOR, there was no reading before bubble point, it means there was no gas libration, which means the GOR before bubble point will be the same as this throughout because it's usually constant before bubble point. Till gas starts to liberate, that's when the amount of gas dissolved in the oil reduces. The next is the viscosity test. The objective of this test is to understand the resistance of the particular fluid sample to flow in varying pressure conditions. So the fluid sample is being collected from the field guys, put it into a rotational or capillary viscometer, adjust the samples to reservoir conditions, and then run it. Measure the viscosities at various pressure steps and record it. And this is how the report comes out. Pressure against viscosity. And the separator test. The separator tests usually simulate surface separation into oil and gas phases to determine optimal surface conditions. It evaluates volumetric behavior of fluids during separation to optimize surface conditions. And the main reason behind this is to maximize stock tank oil recovery. It also provides PVT parameters such as formation volume factor and solution gas oil ratio. Experimental procedure is that you load the reservoir fluid into a separator apparatus, maintain specific separator pressures and temperature, and collect the gas and liquid from each stage and measure the corresponding properties. Analyze the gas compositions and also liquid properties. Integrate the results with the differential libration tests for accurate PVT analysis. And there is the CVD, which is usually done in place of differential libration experiment. That's if you have gas sample. Don't mix it up. For oil sample, you run a DLE, and if it's a gas sample, you don't run DLE, you run CVD. The objective of this is to simulate the reservoir depletion and phase behavior in gas condensates or sometimes some volatile oils, which are near critical. The importance is to determine the retrograde liquid formation and compositional changes. It's also essential for us to have these results so as to build good models and also run production forecasts. The experimental procedure is as follows. You place the reservoir fluid in a constant volume PVT cell, just like the others. You gradually reduce the pressure steps, just like the way we explained the previous ones. Then you measure the volumes and compositions of oil, gas, and retrograde liquid phases. Analyze the phase behavior and recovery potential. Thank you for listening. Any question, guys? Hello.
Yes, sir. Please, I just have one question
Okay.
on the constant composition expansion. You said to get the relative volume. I didn't fully get the ratio. So it's volume for like each step during the compression of the liquid divided by. I didn't really get that ratio to get the relative volume.
To get the relative volume, the formula is relative volume equals to the volume you get of that fluid when subjected to a certain pressure step. You know, I told you the experiment is
Yes.
done in varying pressure steps, right?
Yes, sir.
So at each of those pressure steps, when you subject it to those pressure steps, you will have a different volume of that oil because of expansion. You know, it has a dissolved gas within it. So when you reduce the pressure, the volume will expand. The oil will expand, leading to a slight increase in volume. So you record that volume for each of the pressure step. After recording that, including that of the bubble point pressure, then for you to get the relative volume for each of the corresponding pressure step, you use this formula, relative volume equals to the volume. Let's use 5,000. Let's say 5,000 is our initial pressure. The volume of the fluid at 5,000 psi over the volume at bubble point. Let's say our bubble point is 3.5. So I pick out the volume of oil at that pressure of 3,500, which is my bubble point pressure. Then I bring it here. The volume at 5,000, which is the volume at a particular pressure step, all over the volume at bubble point.
Okay.
You understand? That will give you your relative volume. And of course, the relative volume at bubble point will always be equals to 1 because it's more like 1 over 1. It's some same volume over same volume.
Yes, sir. It's clear now.
Okay.
Thank you.
Olamide Oluwadari. Any question? Pius Honora. Mr. Samuel.
No questions, sir. No questions, sir. Sorry.
So my own question is, so are you going to know the volume at bubble point? Because from this formula that you stated,
yeah,
does that mean the volume that you are going to first get will be the one at bubble point?
No. You'll get it at your initial pressure that you use. You'll record all the volumes for the respective pressure, including the bubble point, first. Then you start populating the relative permeability volumes. The relative volume. Sorry, sir.
So you now start calculating. You first do the record.
You record the volumes of each pressure step from the beginning.
So you then calculate your relative volume afterwards.
Yes.
Afterwards. After you've recorded all the volumes.
After recording all the volumes, then you calculate your relative permeability, maybe on Excel or maybe manually.
Okay, so that's now. So guys, you are supposed to be asking questions. I don't like people that don't ask questions.
Don't ask questions, we don't know if...
Because what I normally see is that people will not know and they will not ask questions. It's either that you are not following. That's when, because when you follow, you surely have questions. Okay, Dimeji.
Yes, sir. So I want to ask about this CCD also.
Okay.
So I want to ask, in doing this, does it mean that we have to hold the temperature constant in the using the reservoir temperature while we vary the pressure?
We subject it to there is a first test that is being done on site. I think I said that earlier.
Okay. Yeah, the primary test. Okay,
yeah, the primary test. They will give you, they will also measure the reservoir temperature, possibly sometimes the initial reservoir pressure, but you have to do your own of the in the lab. So that reservoir pressure, we assume an isothermal condition to run all these analyses. Yeah, there might be some slight changes in the reservoir temperature, but for all this analysis, it's assumed the reservoir temperature is constant. So you subject it to that reservoir temperature, then you vary the pressure. Varying the pressure, it's like you are producing the reservoir. What will happen when the reservoir pressure depletes?
Okay, thanks.
Is that clear? Have I answered your question?
Okay, sir.
Dauda Sunday, any question?
Sir.
No, sir. No, sir. I don't think that.
Sir, I have a question, sir.
Okay, Mr. Samuel.
Okay. From the compositional analysis, the results you showed us, are we going to add the gas and oil together to get the reservoir fluid or what? Because that one, I don't understand how we get the one.
It will come in just as it is like this. You are not supposed to add anything. The only thing you will do is you will QC these values to make sure there are no errors. because it's collected at the surface. The gas has already liberated out of the oil column. So definitely there might be some errors. So you have to confirm that yes, the compositions are completely intact. I believe in the next session, before we jump into the PVT modeling of PVT, we'll do data QC before we start that. But what you really need is the reservoir fluid mole percentage for you to run the analysis. But you can actually use this to QC. So,
okay, hello, sir.
Oladimeji.
Yes, sir. Yes, sir. So my question is, on getting those fluids, are they the fluids that are getting from the core samples?
No. Don't confuse core analysis with fluid analysis.
Okay,
Core
sir.
analysis,
So
we do
that
it
means
to
we
get
get
the
those fluids directly.
representative. We run core analysis while we run coring while drilling to get a representative of the rock within the reservoir. We take it to do SCAL, special core analysis. It's more of reservoir rock properties, not fluid properties. So do you need some explanation regarding the coring and SCAL?
Okay. Okay, no, my question is, how do we get these fluid samples? Like, is there an instrument that extracts the samples?
When they finish drilling the well for the bottom hole sample, they do a drill stem test where they test the pressure of the reservoir. And after completing that, they collect samples. There is a cylindrical column within the drill stem that collects the sample at the face of perforation, and they'll carefully lift it up to the surface and transport it to the lab. That's for the bottom hole sample. For the surface sample, drill the well, complete it, put in facilities, surface facilities, then they'll collect the sample at the separators.
Okay, sir. Thank you.
Any more questions? If you don't have a question for me, I will ask you guys. Just to test that you guys are understanding or not.
Sorry, sir. I just saw something now. Hello, sir.
Okay.
Okay, sir. In those fluid samples, we have some impurities present in those fluid samples.
Yeah.
Yeah. Okay. So we also have some impurities present in them.
Yeah. So you can't have
my question
100%
is
hydrocarbon now. Okay, I'm listening.
Okay, yes, sir. So my question is, those samples usually account for those impurities, both from the samples taken from the surface and that of the bottom hole samples.
Yeah, it's been accounted for because it's within the fluid column. For example, in the surface sampling, nitrogen, CO2, and H2S, all of them come in the form of gas. So definitely it will be within your gas column, the gas you collected. It might be more of hydrocarbon gas, but you will definitely have it dissolved in it.
Okay, sir.
Is it clear? So even for the bottom hole sample,
sir.
the gas has not even liberated. So even the impurities are dissolved within the oil column. So I have a question for you guys. I want everyone to answer it. I'll call names. So why do we need to do PVT analysis? Mr. Samuel. Hello, Mr. Samuel.
Yes, sir. I- I'm here, sir. Good, good.
Answer the question. Why do we need to do a PVT analysis?
Okay, I would say to know the composition of the fluid I want to produce.
Yeah,
Sir?
you are correct, but can you make it a bit technical?
Okay. Okay. I will still say, please,
Let me help
okay,
you. We need to
okay,
characterize the fluids. Is that
okay.
what you mean? What
Yes, sir.
I understood by your statements. Mr. Emmanuel,
You said what?
Mr. Emmanuel,
Sir,
why do we need to do PVT analysis?
hello, can you hear me?
I
I
can
was
hear
muted.
you.
Yes. So like you say, in order to characterize the fluid and understand the type of reservoir we're dealing with.
Okay, that's good. Mr. Dauda, Oladimeji,
Okay.
Sir,
Okay. Yes.
do you have an opinion also?
okay.
Yes.
Yes, sir.
Yes. We do PVT analysis. First of all, to know the kind of reservoir fluids we are dealing with, as that will help us in designing our um, surface facilities. It will also help us to know to design to select our EUR method of production, and also it will help us a lot when maybe we want to kind of select the how to optimize our production actually. So basically, we need to know the kind of fluid we are dealing with so that it will help us uh, design process that will optimize our production.
That's good. Um, Let me summarize it up and sum it up. You have done well. We do PVT analysis, first of all, to characterize the fluid itself so that we can understand the physical and chemical properties of the reservoir fluids. We also need PVT analysis because we use that to help us calculate the in-place volumes and recoverable reserves accurately. Also for production optimization, to predict the fluid behavior and optimize production strategies. Also, we need PVT analysis to do well design, to design surface and subsurface equipment for efficient operations. And as you said, EOR, we also need to understand the kind of fluid we are dealing with in order to design a better enhanced oil recovery process. Also for reservoir simulation, it provides us reliable data for modeling and from data that we use for modeling and predicting reservoir performance and so on. So that is all for today. Thank you all for attending. Looking forward to the next session. The next session will be a hands-on on PVT modeling. We'll start by data gathering. We'll review the data and we QC it. By QC, I mean quality check. Then we model the fluid on PVT. And we end it up by exporting the PVT model. By the end of the next session, I believe all of you guys will be PVT modelers. Thank you very much. Thank you, Mr. Yusuf.
Thank you, sir.
Thank you, Engineer Ibrahim, for this wonderful session. And I see that a lot of time was taken to prepare the slides and also to make it as compact as possible. So what I will advise is that you should share the data that they are going to use
Okay.
for the next session,
So that they can go through it.
so that they will go through it and let them also know what they are supposed to extract.
Yeah, it's the main reason why I dropped an example of how the results of each of the experiments come in. So when they go into the PVT report, definitely it will be more easier for them to locate all those experimental results. Though we'll go through it.
So the other thing is, they might, maybe they will not ask this PowerPoint that you just use. Are you going to share it with
Yeah,
them?
I'll share it to them.
Okay.
I'll share it to them.
Okay. Thank you very much.
Thank you very much. Thank you all.
So
Thank you.
for me, just a concluding question
To me,
that I just want to ask
yes.
the guys,
Okay.
apart from Sunday. So you mentioned that PVT analysis helps you to estimate the volume of hydrocarbon in the reservoir. So my question to them is, how does the PVT analysis help in estimating the volume of hydrocarbon? Sunday will be the last person to answer if it's only if other people don't know. So who wants to go first?
You will not talk. We have to be calling names.
Hello, sir.
Yes,
Hello, sir.
hello. Hello, Emmanuel.
Yes, sir.
Hello.
So are you the one that wants to
Okay.
go first, or who is talking earlier? Or who was talking earlier?
I was talking earlier, but he can go first.
Okay. Emmanuel said you should go first.
Okay, sir. So, for the PVT analysis, looking at it generally, so showing you the reservoir pressure and temperature per time, and having understood the type of reservoir you're dealing with, you can from your plot, from your analysis, you'll be able to get the volume depending on
How
how
will
far
that one help you? How will that one help you to get the volume?
um depending on how far the pressure has dropped.
Mm-hmm. Which pressure is dropped? The pressure, the reservoir, they've not started producing the reservoir when they're collecting the samples. They're just dropping the reservoir pressure. They are trying to like mimic what will happen later in
What
life.
will happen?
So Dimeji,
Okay, sir. So I think part of the to be able to estimate the volume of hydrocarbon reserve from the PVT analysis, I think we need the formation volume test, the FVF, formation volume factor.
so that's correct. So Emmanuel, did you hear the answer?
Yes,
So
sir. Yes.
part of what you get from the PVT analysis is formation volume factor.